Hello everyone, my name is Dishanav Kumar, and today I'll be talking about the threats to machine learning, what I've learned from my papers that I've read through from my panel project. So first, let's talk about the papers. The papers are these six papers right here. Avid Pulse by Universal Segregation-Free and Target Audio Adversarial Attacks via Sub-Second Interpretations. FAIR, enabling fine-grained attack aggregation under low-quality labeled data. Furbus, input regression defense against Trojan attacks on deep neural networks. Next one is manipulating the Byzantine, optimizing model poisoning attacks and defense for federated learning. Simahan, IPv6 address correlation attacks on time to TSL encrypted traffic via Siamese heterogeneous graph attention network. And then WaveGuard, understanding the mitigation auto versatile examples. So first, let's talk about AvPulse. AvPulse is overall, this basic of this paper was that the authors wanted to further study the attacks against smart speakers. Things like these smart speakers are also your devices that can understand human voice commands and perform some sort of command, such as Amazon, such as the Amazon Echo or the Google Home, or even your virtual assistant on your smartphone. The way an audio adversarial attack would work, though, is that the authors of the paper would play some sort of interpretation, some sort of unlegible or unhearable video file that would modify the pre-recorded speech or the actual speech of the user saying a command, modify it, and then it would be read by the intelligent auto system, but it would make some sort of different kind of command. So they actually found out by doing this is that they were even able to add the interpretation even when it was a small amount, so it wasn't even fully part of the entire synchronization of the entire speech line. And they still able to put like one small perturbation inside there, and that actually was able to attack and change the command itself. So we can already see here there's a threat. There's already an attack towards smart speakers or in general speech recognition machine learning by poisoning or by changing up the type of input it accepts. It can then make it produce some sort of different output. Next paper. Next paper is FAIR. In this paper, they wanted to find a solution that can better improve the performance of machine learning models when the input dataset either has some sort of missing or incorrect labels. So we all know that input when it comes to input or creating our models for machine learning, the input must be clean or at least have the proper labels, or at least be sanitized in a way where the data doesn't have any kind of outliers or any kind of missing values, as those values can usually mess up or could make a model fail to learn or make it have issues to actually learn. So that's why FAIR was used. Is basically a clustering method that uses ensemble machine learning, so multiple different types of machine learning models to get some sort of fine-grained attack categorization. So the overall the overall idea behind this machine learning model is that initially they wanted to improve the performance of it because they wanted to better identify attack models or different attacks on for security threats. And usually those kind of attacks don't really have a lot of correctly either have missing labels or incorrectly labeled labels. Um, but with FAIR, the model was able to categorize the input database into or dataset into fine-grained clusters, so that even though the input data had low number of defined fields, it could still be categorized or still be categorized based on the type of labels it has, or at least it can be detected by FAIR to pretty well accuracy to actually know which is an attack and what is not. For this machine learning model for FAIR, multiple different unsupervised machine learning models were used to create an assembled model out of them. In this case, it was k-means, db-scan, and then the DC algorithms. They're all used to actually create a assembled machine learning model that can easily identify um, a threat model or a threat attack, even with when the labels were very mislabeled or not even there, incorrect. Next, we'll talk about Furbus. So Furbus was, in this paper, they wanted to investigate new types of defenses, concepts to aid against Trojan attacks on deep neural networks. So a lot of the examples shown in this paper is that there were examples where Trojan attack could effectively modify the input or modify what in this case, they showed self-driving cars because because the deep neural network they were using or that they took the example was to look at self-driving cars, and then the and actually being able to look at those street signs. So they propose that the idea that by these Trojan attacks, they can effectively poison and modify the input. So in this case, for example, in the example we see here, it could trick a self-driving car image recognition software to think that a stop sign, which normally makes the car stop, is actually is actually a speed sign, or at least a speed limit sign, meaning that there was no stop sign, which could potentially mean that the car, if it didn't know any better or if it was being attacked, could potentially run through a stop sign and maybe even hurt someone. Um, so to counteract this, Furbus, what it did is it utilized input sanitization to sanitize the affected inputs by exploiting the biases that the Trojans would leak. So there obviously whenever a Trojan attack would happen, there was some sort of like bias that would leak from it, and then the neural network, and then the Furbus was able to uh, exploit that, or at least analyze it, find the exploits, and then or find the biases, exploit them, and then it could then further localize the affected part of the Trojan tag and then remove it, and then restore it as well, as is shown here as well. As you can see again in the second part of the image, even after a Trojan input, the Furbus system allows is used to analyze the input, see detect where the Trojan bias is, remove that, and then restore it, and then put it back into the and then put it into the deep neural network before it has been inputted and potentially messes up a prediction. Next, we'll talk about model poisoning attacks defense. So our other paper talked. They want to talk more about the idea of they want to explore more about poisoning attacks on federated learning models. And what is a federated learning model? It's basically a joint machine learning model that trains data over through multiple data owners, so multiple people actually can train the model together. Um, while still not well, actually they don't need the client's private data. So it's kind of think of it a way as like a machine learning on the go, or a group machine learning training session where multiple users can upload data or upload training data or upload these new updates to the model to better make it learn. Usually, these types of models are used in live settings where people are usually using their cell phones or are needing or need to go outside and upload live data to the model, and that's where the best use. So they did in this paper. They did look at both attack methods and defense methods against federated learning models. The attack method, or the tactic that they notified or they showed, it was used by used by using benign data samples to compute a benign reference aggregate. So obviously something that is can be benign that they can obviously predict that would normally aid the model. But afterwards, once they've created that aggregate, they would then create a perturbance vector that would try to push the aggregate in the opposite direction. So normally the benign, which is the good data, would push it in the correct direction, but then they would create a different vector to push it in the opposite direction. Therefore, by poisoning it and making it potentially give the model of a wrong prediction or wrong train value. Once they've created the vector and then pushed the aggregate down, they would then upload that update to the reference model, to the joint model, and then theoretically that malicious update would poison the joint model and make it have a worse prediction. And it was shown that in this paper that anytime they did try to do a poison tag, it was almost always accepted, and it did affect the performance almost 100% of the time. Counteract that in the defense tactics they use to kind of counteract these kind of poisoning attacks is they use something called a verbose aggregation algorithm, which used spectral analysis to detect and filter out any outliers in the potential poisoning data. So obviously, whenever the model would run, it would check to see all the multiple different types of data it's accepting, and if it noted that one of them was an outlier or potentially could have been poisoned, it would remove that data set and would not use it or filter it out, and would not use it when creating the joint model. Okay. Next paper is Shibahan. So Shibahan is a little different, where they wanted to look at the possibility of finding out a person's internet access or internet activity over the internet um, by using Siamese heterogeneous graph attention networks, as you can see here in the image right here. Basically, by using this type of machine learning, they're able to using node level attention and graph, kind of in a way of like creating using networking to figure out from the address overall the IP addresses of the network, even if the IPv6 addresses were masked or did not were not known to the user or were not known to the adversary, they could still use this algorithm to theoretically map back or to give a good guess of who is actually on this network or who's actually through the traffic, even if the IP addresses change. Okay. And finally, the last people we'll talk about is waveguard. So waveguard, similar to the other one as Avipulse, also wanted to look at adversarial audio attacks, where obviously some sort of speech or some sort of malicious speech would be said to a speech recognition model, and then potentially give a wrong command, right? So in this case, but on the other side is that with waveguard, they decided to create some sort of fence against it. Um, in this case, they utilized audio transmission functions to analyze the transcripts from automatic speech recognition deep neural networks. Um, both of the original and the transformed audio samples were analyzed, and in this case, they were basically the waveguard would use its own machine learning model to detect whether if a audio input is malicious or benign, as shown right here, right? Normally, you would use some sort of like machine learning model to detect between whether to basically give a best guess of whether if the input is benign or adversarial, and if it's obviously if it's benign, it lets it go through to the speech recognition model. But if it is adversarial, then it usually will separate it or it will create an alert saying that this is an adversarial attack, and it would not add it to it would not let it go through to the speech recognition model. Okay, finally, now let's talk about what we've learned so far. As we can see from the papers, all of these papers have talk about machine learning, and we all know that machine learning is a tremendously useful tool for the sake of creating predictions on live real world data. But obviously, when it comes to a good opportunity tool like this, there are usually malicious adversaries who will try to attack such a good tool. In this case, we've seen that a lot of malicious adversaries will attack the model to degrade their performance, and obviously the most popular types of methods is to poison the input. We've seen a lot of times where anytime an attack was made against a machine learning model, the model itself wasn't attacked, but instead the input that was given to the model to train it was instead attacked or was been poisoned. And it seems like there was no the way the attacks worked is that they would simply make the input not optimal, or they would purposely give wrong input or modify the input where they would purposely wrong, so the model wouldn't be able to learn from it or wouldn't be able to learn properly, and then would provide wrong predictions afterwards. Um, in a case when it comes to threats, when all the attacks against all those virtual attacks, we have seen a couple of defense tactics. Fair and Waveguard were both two types of methods that were proposed that could purify and detect malicious input, and either to remove it or to alert you that there actually was is uh, an attack against our model. So as we can see, overall, it seems like the biggest threat to machine learning models is basically its own whip input. It is paramount that when you are building these models, you have to make sure the input is clean or is at least properly formatted, but also when running the actual model itself, especially if you're running the model in a live setting, like a federated model, you have to make sure that that there's some sort of safeguard in place to scan and possibly purify or at least alert you if there's any malicious input coming into your model. All right. That was my presentation. I thank you all for listening, and if you have any questions, feel free to ask me.